Shelley, you give a reason why you could do it. Can you give me a reason why it's preferable to treat the dynamics of the wave function on the covering space?
Well, we know physically that we know, well, that would be good to say that it's inevitable. The main argument for that, I guess, is we know we need fermions, of course. That's not satisfying, but and you know, the standard answer is now you need to go to quantum field theory. From a non-relativistic point of view, non-quantum field theory point of view, that why it should be maybe Roddy can say something about that. There could be something to be said, but offhand I don't know what to say. It's simply a natural possibility.
Can't you just say you need identical and non-identical particles in your theory? This is another way of saying you need.
But that doesn't lead you to fermions.
Ah.
If the question is why do you have the natural why must you have fermions? You have an answer?
No, I don't have anything particularly useful to say.
The only thing I can say is why
You
not?
have to bring spin in. I mean, presumably you'd have to. Nothing's been said about spin.
That's right, and we
so
were thinking about why
you
spin
would
would
expect
force
there's
it.
got to be some connection.
Well, we were even trying once to figure out why when you do consider spin, something better happens when you allow for the possibility of fermions and bosons. I don't think anything really worked out there. But my memory is right. Roddy will remember better than me.
That's right.
Both things are right.
Shelley, part of the worry I had was I just didn't know with the strange topology, would the evolution of the wave function be at all tractable or
Well, you see, the fact that
the wave function lives in a space where the topology is simply connected. It's
no,
not
where it's not. No,
no. You see,
that's what we're talking
the
about.
way you deal with strange topologies is often just like I'm describing here in mathematics. It doesn't have to be quantum mechanics, whatever. You have some object on some field or function on a space with a strange topology. You say, that's a hard thing to deal with, a strange topology. Let me lift everything to the covering space. Then I don't have the strange topology anymore. I have some consistent. So that's what you would do.
Right, and you put boundary conditions on it.
Yeah, you put boundary conditions on it. The boundary conditions in that case would be symmetric or symmetric objects usually, but here anti-symmetric is okay too.
okay. So it's very interesting. So am I right in thinking that this way of thinking about things in terms of the unordered, the set of unordered pairs out of, say, in the case of two particles, out of R3, that representation is not, the Bohm theory that you then added is not an option. That representation then, in order to then get what you need back, which is going to be, because it matters that there are anti-symmetric states. You can do scattering experiments where you get interference effects that are coming out of anti-symmetry. So you need that. You need to get something. You need to get that back, and you only get it back with it. The Bohm theory isn't an add-on, right? It's all part of. You can't have this package without Bohm theory. Is that right?
I don't understand.
You don't understand the question?
No.
So, well, I was saying, when Tim told his story, right, and then I said, and now tell me about symmetry and anti-symmetry and the difference between bosons and fermions, because that was there in my original quantum mechanics, and I'm trying to reconstruct it. And at that point, you took over and said, well, go to this covering space, put wave functions on, consider groups, permutations, get symmetry and anti-symmetry, and you're back where you started, okay? And that was all told in terms of the connection between the particles in the 2R3 and the wave function coming out of the equation of motion, so it's a Bohmian picture. And so I'm just trying to check that that there's no other way for you to get back to the distinction between symmetric and anti-symmetric statistics that you started with from Tim's picture without adding the Bohmian stuff.
I think you need a precise picture of quantum mechanics. Maybe not necessarily Bohmian,
okay.
Maybe another precise picture.
So it could be something.
But I should say that this was first done. Look, suppose you're a normal physicist. If you're a normal physicist, you think, if at all, rather vaguely about ontology. When you talk about configurations, you think you have points in R3, you know they don't have positions, so what you're exactly thinking is not so clear, but you write down Q1, Q2, but you probably have any sense that the labeling is not really significant, particularly for identical particles. So you naturally might be led to the thought you should have the natural configuration space is something like that. And people did that, and then people probably worried about to deal with fermions, and they did stuff. What were the names of the people? Linus and there were some more people.
Schulman also started.
Schulman, that was from a path-angle point of view. A variety of people, from a variety of points of view, did things very similar, and they had topological ways of getting back fermions from it. Fermions, of course, going to be a little more problematical.
The names are Linus and Merheim.
And there's a bunch of other people. Who's the Everett guy who wrote in physics? DeWitt. Is it, which one? Maybe it was his wife, Cecil, or is it Price? Who?
Cecile DeWitt, but she did it, I think, after Schulman. Cecile DeWitt.
In any case, you can do this from a more orthodox point of view. Whether it's as well motivated, well, I would argue it's not as well motivated. They would deny that because they like the non-orthodox, their usual orthodox point of view. To me, what's particularly nice about it, from a Boolean point of view, is it seems very well grounded in principle, number one. And number two, we're usually told that exactly this kind of possibility of fermions is impossible from a Bohmian point of view. You need to get rid of the idea of particles with trajectories to have the possibility of fermions, which is just completely wrong. And by the way, there's a similar business class which usually denied. No, not usually. It's often denied that classically. It's often said that classically you must think of the particles as indistinguishable, and that statistical mechanics, Gibbs paradox, sort of tells you that the world must be quantum mechanical because you have to treat the particles as indistinguishable. And that's wrong. People sometimes quote Gibbs for that. I don't
Let me ask, Shelley, you said that in classical mechanics you have to think of the particles as indistinguishable. I think you meant as distinguishable.
Because of
Could you say again what you meant?
People said that some people say that because of the Gibbs paradox, the Gibbs paradox teaches us that the particles must be metaphysically regarded as indistinguishable, unlabeled, and so on, and therefore, classical mechanics is wrong and must be replaced by quantum mechanics. And I
understand the therefore part.
Because classical mechanics has not the resources for handling such a situation. Just treated it that way.
And Gibbs was somebody I recently saw a paper where somebody was doing that. Gibbs was cited. The guy was really nice. He cited the exact pages in Gibbs, Elementary Principles of Statistical Mechanics. But what I found Gibbs writing there was perfectly reasonable and not at all providing support for this conclusion.